explain, or I don't really have any plans. But let's see, how are we doing audience-wise? Okay, I think that people will start joining now, and maybe I should introduce you, and we can get started with the talk.
Okay.
So it's my great pleasure to have Ábel Garab in the webinar today. So Ábel is currently an assistant professor at the University of Szeged in Hungary, and he is one of the world experts in delay equations with cyclic feedback properties. So today he's introducing to us something completely new in the form of some sort of Lyapunov function for cyclic feedback systems with even state-dependent delays. So Ábel, the stage is yours. Thank you very much.
Thank you very much, Alejandro, for the introduction and also for the invitation. So, as Alejandro said, I'm going to talk about cyclic system of differential equations with constant time variable and also state-dependent delay. And this is joint work with my colleagues in Szeged, István Balázs, Ferenc Barta, and Tibor Kristin. So this is just the outline. So first, I will talk in general about cyclic system of delay differential equations, how it started by Malé-Paré and Sell, and what is already known, how we tried to, or not tried, but how we generalized some of their theory. And then, this is not in chronological order, by the way, but I will talk about then some less new results on the cyclic system of delay differential equations with constant delay, then some about state-dependent delay in the scalar case when there's not a system of equations, just one equation. That's the last part. Okay. So how is this meant to be a cyclic system of differential equations? As you see, maybe this one, the very first one, you see my cursor, right? So yes. We have 0, 1, and so on, n, so altogether n+1 equations. And the ith one depends on the change of the ith component, depends on itself and time, because that's non-autonomous in general, and on the next node, the next variable, xi+1. And here we mean xn+1 means then the x0, just to make the formalism easier. So if we take such an equation here, this is not time dependent or anything, this is just constant at the moment. And you can normalize such equations in a way, so after with a transformation, you can get to this form, a different feedback function, not g but f, because of the transformation, and then you will only have one delay in the last one. This is where this cyclicity is important. So if there would be any other connection in between other than these, then it would not be possible. Well, to be perfectly honest, it could be bidirectional, but we don't consider that. So this is a setting that was considered by Malé-Paré, John Malé-Paré and George Sell in 1996 in 2 joint papers, which are very important in this field. And in their work, it was allowed to have bidirectional. So here, connection. So here you would have, you could have xi-1 t. So an instantaneous term xi-1 t in almost all of them. well, actually in all of them but one. So anyway, we consider this unidirectional cyclic system. So in that sense, somewhat less general than their setting. But what is, sorry, just have to remove something from here. Okay, so I'm sorry, this should be a tall. Okay. And you can also, so you assume that there is a feedback condition in the second variable. So either you have a positive feedback like this in all of the feedback functions from 0 to n-1. That has to be a positive feedback, and in the last one you can have either a positive or a negative feedback, which is reflected by these conditions. So this is meant as this is strictly positive, the derivative is at 0. This means just the derivation with respect to the second variable d2. That means only that. It's not a constant or anything. Yeah. And this is negative when this is negative, okay? And so in the original setting, you could have either positive or negative in any of the functions in arbitrary order, but you can normalize this in a way that you will have all positive feedbacks in all but the last one, and either positive or negative in the last one. Okay, so it also follows that the origin is an equilibrium point, so it will be important to some extent. We will be counting actually the number of sign changes somehow of solutions on certain segments. I will show this in a moment. Okay, so just very briefly that this has many applications. Such equations, they arise in various models. I'm not going to show many concrete models, but I just flash some there are many applications in biology, physiological model, neural networks, economical models, and even in traveling waves, they somehow appear. So as just a toy example or a concrete example, you could consider this equation. So a tangent hyperbolic, for example, it's a sigmoid function, but it doesn't have to be, like I already mentioned this before the talk to Alejandro, so it doesn't have to be monotonous, the feedback. Okay, it has to keep its sign on each side, but otherwise, in the second variable, but otherwise it doesn't have to be monotonic. Okay, for example, if you consider a second order position control model, so let's say we have this toy model, we have an object here or somewhere at time t, we have it here. Here's a wall, and here's this target, I don't know, the origin, where we want to make this to move somehow. And we don't know where we are, we don't know the position, but we try to get some information by using echo or something like that. So we send a signal to this wall. In between, we move in some direction, and then we receive this reflects, the wall reflects our signal, and then we get it back. So, and then it takes some time until it gets to the wall and back. So when we ask, okay, so maybe in the other direction, so from here, yes, gets to the wall and back, but when we receive the signal back, we're not there anymore. And we want to somehow adjust our velocity based on the on this information, which we can well calculate, or more or less calculate where we are, if we assume that we hardly moved. So in the sense that the wall is quite far away, so the signal has to travel some, but it doesn't really make a difference whether it's sent from here or from here. So it has a constant delay. And then in any case, we will receive the information where we were tau times prior to our to this. Okay, and we will make our decision somehow, or make our control based on that information, so we can adjust our acceleration, for example, whether to give gas or to push the brakes based on this information, and somehow we want to get to this origin. So then we will have such a cyclic system of equations, for example. But if we want to make this, actually, if we want to make this more realistic, if this counts where we receive this, so if our velocity is somehow comparable to the velocity of the signal, then this tau will be state dependent, if we cannot neglect this distance between these.
Ábel, can I ask a question really quick?
Yes, of course.
Because when I talk to people about state-dependent delays, they always come up with the example of a bat hunting for food, right? So this would be a little bit like this system, right? Like your block here is the bat, and the bat emits some wave, and then it receives it back, and then the bat echolocates, right? Maybe the bat is looking for a fly or something, I don't know. So, but I always find it really hard to understand that the velocity of a bat can measure itself to the velocity of sound somehow. Like sound seems so fast compared to the movement of any animal, right?
Yeah, but it depends on how far this this object or this wall is. So well, and sometimes, well, so certainly you will have a small delay here, and it to some extent for sure depends on the state. Whether you can neglect this or not, that's a matter of, yeah, can depend on the velocities and the magnitudes, but it's just a matter of taste, what you decide to neglect or not.
For example, for lasers, I think that it's very clear you need to account for the delay. Yes, thank you.
Yeah. Okay, so it's just an example, and now I want to clarify, or I want to explain a very basic tool introduced by John Malepara and Cell, and actually this is what we're going to generalize in the first part of the talk. So speaking of still constant delay equations, first of all, a possible phase space or a natural phase space for such equations. So you have to have an initial value problem. You have to keep track, or you have to have the zeroth component defined on a tau long interval. Of course, you need it in minus tau, for example, for t equals to 0. But if you integrate further, you will need it for further times until 0. So you have to keep track of the zeroth component on a segment, on a tau long segment, and all the others just in one point to start integrating. Okay, so the natural state space is the continuous functions defined on an interval plus endpoints. Okay, so this means the zeroth component on a, well, here tau is 1, so on a tau long segment, and then 1, 2 points. So this is in the n equals 2 case. Okay, so here comes the interesting part. What John Malapart and George Sell figured out is that if you count the number of sign changes on such a member of the state space in this way, that you consider this as if this would continue somehow, and then, well, with a, if we would connect these 2 points, the end of this segment and this point, with a straight line, the question is whether it changes sign or not, and then again whether this changes sign or not. So okay, we count the number of sign changes. Here we have 1, 2, 3, 4, and here the 5th, somewhere in between, and here's no sign change. So in the positive feedback case, you count the number of sign changes, and if this is an even number or infinity, that can also be, then you just leave it as it is. And if it's an odd number, then you add 1. So you round it up to be an even number. And okay, sorry, I haven't clarified what this x sub t is. So this is the state at okay, here it is. Yeah, so you just push it back to at time t, you push it back to the interval -1, 0, and that's how you get the x sub t. Okay, so you will have in this case 5 sign changes. So this v is defined to be 6 for this member of the state space, because that's an odd number, so you add 1. And if that was a positive feedback case, then we will have 6, v equals to 6. And what's interesting about this is that this turns out to be a non-increasing function along solutions. So therefore it is called a discrete Lyapunov function. And in the negative feedback case, you have something very similar, but then you count the number of sign changes just as it is here. And if it's an odd number, then you leave it as it is, and otherwise you round it up to be an even number. An odd number. Okay. And here's the theorem statements of Malapart and Sell from 1996. So, like I already told you, this is along solutions, non-trivial solutions, because for the trivial solution it is just not defined, the v, or the Lyapunov function. So it's strictly non-increasing. Yes, okay. So it's non-increasing, and it has very nice properties, which we will somehow, which are very useful in many ways. I will give some hints about that. So it's lower semi-continuous in general, but there is also a dense open set in the phase space, and even a part of that that's even a part of subspace of this phase space. So where you not only assume continuity of the function, but C1. So open dense set of C1 functions on which it is continuous. And that makes much easier any application, any analytic application of this Lyapunov function. And what makes this even more applicable is that you can guarantee many times that this is part 5, that the function, that the solution has already reached, or it reaches this R for regularly behaving solutions. Namely, if this V value doesn't change for a while, so if it's the same value for t and t minus 4, and it's not infinity, then you are already in, at time t, you are already in this set R where it is continuous. And since so if you have, for example, an initial state where the number of sign changes is finite, so of course here it is only finite, it can be only finitely many sign changes, but on this continuous part there may be infinitely many. There could be an accumulation or more accumulation points of zeros. So if you start from a segment which is or a state member of the state space which has only finitely many sign changes, then if you continue this solution, if you start a solution from this and you continue it until infinity, then you will never have a solution that has infinitely many solutions, infinitely many sign changes. And moreover, this number can only decrease. So after a while, and it takes positive integer values, or at most it can be 0, but definitely bounded from below and discrete. So you, after a while, you will reach a finite, a final value of this V. Okay, so the limit at infinity always exists in that case. So after a while, you can guarantee that solutions will be in this set R. Okay, and there's also a condition which gives us hints when this has to drop. So if you have two, the value of V has to drop. So if two consecutive values are 0, so for example, if this and that would be 0 at the same time, or if this and this would be 0 and this would be 0, they're also consecutive, considered to be consecutive, then there has to be a drop somewhere between the t minus 2 and t times. Okay, it has to decrease. Okay, so these results have, according to Google Scholar at least, 200 citations, which is quite a lot for such a analytic and such a not very so to say applied theorem. It's very, very general, and it has like 200 citations. It has many fields in the dynamics where you can use this, proving, for example, existence of periodic solutions. I just listed some authors that use this, but I'm pretty sure that there should be at least 2, 3, 4 times more to list. So you can also, that is also was the companion paper by John Malipari and George Stell, a Poincaré-Bendixson type result for monotonic, when you also assume that the right-hand side is monotonic in the second variable, then you can prove a Poincaré-Bendixson type result, and this was generalized by well, at least for scalar equations to some extent by Benjamin Kennedy. Okay, it is also related to Wright's, the famous Wright and Jones conjecture. And it was also possible to give a full description of the global attractor in the scalar case with monotone positive feedback that was done by Christine Walter and Wood. A whole monograph is written on that such equation, and these conditions are very heavily used. Okay, and that's also possible to give a structure, give some insight into the structure of the global attractor, and in particular, Morse decomposition of the global attractor can be given based on such arguments in many cases. And this was, well, actually, this was prior by Mallet-Paré. This was prior for to this prior to this result for at least scalar equations that Morse decomposition of the global attractor exists, but he used the same kind of properties for scalar equations. So for less general, I quoted here the general result. Okay, I will explain to you what the Morse decomposition is, don't worry, because that's one of the topics of this talk. Okay, and it's also related to the Mackey-Glass equation, and although that's not monotonic, but yeah, in general, this isn't as well. Okay, so motivated by this, and also by seeing how many applications it has, we thought it would be interesting to have this for equations where this we don't have a constant delay, but something more complicated. Okay, so let us consider a time variable delay here. So we already considered the normalized equation, and then we plug in here, instead of tau, a tau t. And let's say a few words about state-dependent delays already. So if you have a solution to let's say we have a tau of x sub t, that's a state-dependent delay. So it might depend on the state, but not on t. So here, well, not on t directly, but on the state x of t, x sub t, sorry. Okay, so if you have a concrete example of a concrete solution, an entire solution, let's say, then of course x of t is just a function of t. So then the compound function t of x sub t is just, it can be written as a, I don't know, eta t, or not, let's say not eta, r of t. Okay, so then you will have, for that concrete solution will definitely solve such an equation like this with a time variable delay. And if you can say some very general results about time variable delay, what all solutions fulfill, then you have already said this, or you have already proved this for state-dependent delays, right? Okay, so in this section, I will only talk about time variable delay for that reason. Okay, so again, we have the usual feedback assumptions, which I don't repeat here. So we just replace this here with a time variable delay. And we assume that this tau is continuous, strictly positive, and bounded by some r. And oops, sorry, I forgot to replace this. So eta, I will use the this notation eta, that's the delayed term. So I thought I have already replaced this. So t of t minus tau of t, that's eta of t. Okay, so the delay term, so this t minus tau of t is assumed to be strictly increasing, and that's very important. Okay, well, coming back to state-dependent delays, it is not obvious what the conditions are that has to be met. So we have t minus this tau of t strictly increasing. But I will give you some examples in the end, which fulfill this. But in general, the in practice, in all concrete models, or this is almost always the case that this is fulfilled. So, okay.
Abel, may I ask a question before we get into more complicated stuff? So eta is eta of t, right? It's a function.
Eta of t, yes, that's t minus tau of t. Yes, sorry.
Okay, so it's not x0 of t minus tau t, but t minus tau t.
No, it's t minus tau t. Yes.
Okay, so only the interior argument. Okay.
Yeah, it's just the delayed time, not the delayed term x of yeah. T minus tau of t is increasing. Yes.
I see. Thank you very much.
So it has nothing to do with the solution.
This has to do with the derivative of tau, right? This is like tau prime is smaller than 1.
Yes, if it's differentiable, yes. It doesn't have to be differentiable.
Oh, of course. Thank you.
Yeah, thank you for the question. Sorry for this typo. Yeah, made it harder to process. Yeah, so the thing is that now we can define a similar way a function v. So we just count the number. So if you have any a, you can count the number of sign changes of a function that is defined on it, on this a0 and in this point, and then you count the number of sign changes exactly the way it was, and you just add 1 if it was odd in the positive feedback case, and similarly in the negative feedback case. And we can also generalize. So with that, we could generalize this function v, and we can also naturally generalize this set of regular functions. And of course, the theorem is that this generalization makes sense in a way that we have all the properties, basically what we had for the constant delay case. We have an analogous counterpart in this time variable case. I don't read all of this, but these are just generalizations which are somehow natural, but you can also prove them. That's the good thing, or the good news. Okay, and so we hope that we will have maybe not as many, but at least some applications as the original one. So maybe just some initial idea of the proof, which gives you some hint on how this goes, is and here it is what we use, that it's unidirectional. It makes things somehow easier because the original paper was like 50 pages long and quite tedious proofs, and so it doesn't change so much in the sense that it's still tedious calculations, but maybe not that long. And what helps a bit, of course, the time dependency makes it worse, but what helps a bit is this unidirectional nature of this system. And if you define here A i's and B i's this way, then you can see that if you have an entire solution, or actually any solution of the original equation, I mean, by original, I mean this time variable with the time variable delay, then it also solves such a linear, also non-autonomous equation, where here, as always, the x n plus 1 t means the x0 t minus tau t, okay? And this can be, we can go one step further, and by defining ci such a way and yi this way, we can see that this y will solve also linear equation, but and cyclic non-autonomous equation. So this is not a transformation in the sense that, okay, so we don't say that their solutions match, but we have that y solves this equation, and it has it's strongly related to the original x, because we can see that x and the xi's and the yi's have the same sign. By definition, one can say this. One can also prove with some work that if y of t is in this regular set, then, okay, then again a typo, I'm very sorry for this. This should be an x sub t. An x sub t then is also in this regular set. And what makes this much easier to consider is that because of our feedback conditions, these CIs have constant sign. In fact, all but the last one are positive all the time, and the last one is either always positive or always negative. And then you can imagine if you have some information about the sign changes of xi, that gives us information. For example, if you have two sign changes of xi, then also the derivative must change sign. That's quite clear, because it has to have some monotone increasing part and monotone decreasing to change sign. And then if this changes sign, this means that the xi plus 1 must also change sign. So I just wanted to give some hint about how you get these sign changes from one another. And then it's still quite tedious calculations. It's elementary, but still not highly non-trivial, I would say. Okay, so this is just some hints about the proof. So we could generalize, and this is very new, so this is not yet submitted. We hope to submit this early next year. All right, so how can this be? Well, in general, not just the time variable case, but in general, I would like to show some examples how this can be used for, I mean, even in the constant delay case, how these properties, where are they? These properties, where they are used. I'm not going to show you how exactly, but just give example where they are used. And for example, in constructing a Morse decomposition of the global attractor. So I just want to define everything that is included in this. So what the global attractor is and what the Morse decomposition is. So for example, if you have a semi-dynamical system, you know what that is. Okay, I can hopefully skip this. Entire solutions. So we have the global attractor given a semi-dynamical system. What the global attractor is that reflects the long time behavior of the system. Now we're talking about normal global attractors and not pullback attractors. So these are related to the autonomous case, but we also have some results related to pullback attractors and the non-autonomous case as well in this direction. But now let's keep things easier and let's just talk about the normal semi-dynamical systems and not processes, and therefore global attractors. So it's a compact invariant subset of the state space, and it has the property that it attracts all bounded subsets of X in that sense. Okay, so this is the global attractor, and it has the characterization in very general for any semi-dynamical system that
may I stop you for
yes.
a moment, Ábel? So
Yes, please.
We are now doing time-dependent delays, right? Or is this
no, not well.
Time-independent case?
No, this is not in that case.
Okay, so we are still in the
now we're yes, but still, if you have even if you have a time-dependent delay, but no time dependency here. Okay, so if F is independent of time, so it's autonomous, and you have a bounded tau R, then the state space can be taken as independently of the delay. Can be still this CK. Okay. So the right hand side has to be independent of time.
I see.
Or it can be depend on time, but then we will have a process, and we also have some results on that. For example, we can give, this is also very recent, we can also give conditions under which we can prove at least that on the global attractor or in the process case or in the non-autonomous case, on the pullback attractor, you don't have this super high frequency solution, so where this number of sign changes is infinity. Not on the attractor, not on the pullback attractor at least. But now let's stick to the case when, where am I? Where we have constant delay and okay, constant delay cyclic system. Okay, so the attractor, the global attractor, can be characterized as the points of any bounded entire solution. And now what the Morse decomposition is, the global attractor may have a Morse decomposition, which is a finite ordered collection of disjoint compact and invariant sets that are called the Morse sets. So in what sense are they ordered? They are ordered in the sense that if you take any entire solution, here it's denoted by phi, and any point of this entire solution, then the omega limit set of this point has to be in one of the Morse sets, the alpha limit set of this solution, because we don't have backward uniqueness, so we can only take this in general, the alpha limit set of a concrete entire solution and not of a point, where at least this is how we define it. So this is all also in a Morse set, and then this I, where the alpha limit set is, has to be greater or equal than J, and where MJ is the Morse set where the omega limit set is. And if they match, if I is the same as J, then the whole and this entire solution runs in this the very same Morse set. And this is a decomposition because together with the connecting sets between the Morse sets, we get a decomposition or a partition of the global attractor. So to give you some more idea about how this looks like. So these are the Morse set. So if you would go far enough from this picture, when these would be just points, these ellipses would be just points, then this would look like a global attractor of a gradient system. So in normal gradient systems, you have a natural Lyapunov function, and that's a normal Lyapunov function, not like ours. And the equilibria you would see in this structure, the equilibria of if there are finitely many, that would give Morse decomposition. And since we also have some kind of a Lyapunov function, but it's discrete, probably from there comes the idea of Mallet-Paré and cells, that it also should have some similar structure, and these sets should be then the level sets, more or less the level sets of this discrete Lyapunov function, and that's exactly the case. I don't think I really have time to go into this. I just wanted to give here an example of Morse decomposition. In any case, this is just to show that Morse decompositions are in general not unique. So it might happen here. I gave two different Morse decompositions. Both of them are, this is just a 2D, no delay, very simple equation. Just wanted to give some hints about how Morse decomposition may look like, in where one can understand it. But in general, this also shows that it is not unique in general. And for example, if you just take the trivial decomposition, you take one Morse set, and that's the global attractor itself. It also gives you a Morse decomposition by definition, but it's not very interesting, right? Okay, so it also gives us some idea that it may be more or less fine. This decomposition, you may have more sets or less, and even if the number of sets are the same, you may have different decomposition. You may get a different decomposition and different, even different connecting orbits. Okay, so in this direction, probably the first result was again by John Mallet-Paré from 1988, where he considered such scalar equations with constant delay. And here again, the Morse sets are basically the level sets of the Lyapunov function. In that case, this is also allowed. This is when you only have one equation. Capital N is equal to 0 in our setting. Okay, then later on, so this was for negative feedback. Then later on, Monika Polner did the same, achieved the same results more or less for positive feedback. And we also had, with Christian Pötsch, a result for discrete equations, so discrete time equations with delays. It is also possible to get an analogous result for the global attractor. Morse decomposition can be defined and proved. Okay, so how this Morse decomposition looks like, and here is our result for or my result for the constant delay case. So again, we're in this setting, cyclic system of equations with constant delay, and this is autonomous now. So if you count the number of eigenvalues with positive real part, you call this M star, and then if the zero is the zero is non-hyperbolic, the origin is non-hyperbolic, then you add 1, otherwise you just keep it as it is, then you get this value N star. Okay, so what you get is basically that the Morse sets, that there's a Morse decomposition of the global attractor, provided the global attractor exists. Then you have a Morse decomposition of it, where technically these Morse sets are very analogous to the results, to the ones seen in Malley-Paris results. Namely, there are more or less the level sets of this discrete Lyapunov function. Okay, like I said, once a global attractor exists, but you can easily give conditions, some dissipativity conditions for that, which guarantees that. Okay, so that's one of my recent results. Somehow the date is missing. Sorry again for the typo. That was from 2021, I think, which was published in JDE. So what are the main ingredients for the proof of such a Morse decomposition? So first of all, you need this discrete Lyapunov function. You need those properties about semi-continuity, about where it's continuous, where it strictly drops, and so on. And on this, you need this regular behaving set of regular behaving states, and you also need knowledge on the linearized equation, because with that information, which was also available thanks to Malley-Paris and Cell's paper, you can you know the values of each eigensolution, you know the V value, and then you also can know the sums of such solutions, for sums of such solutions, what the V value is. And with the help of knowing that there are no super exponential solutions on the attractor, I will explain in a moment what they are, you can connect these information. You can prove that similar things happen for the nonlinear equation as well. So the super exponential solutions are those that converge to zero faster than any exponential. And if you exclude them, you can relate, you can capture the behavior of the nonlinear equation by the linearized equation. The asymptotic behavior can be captured only in that case. And this is done in this paper, and also the Morse decomposition for cyclic system of equations with constant delay. Okay, a final goal in that case could be to generalize this result for state-dependent delay, and also it would be very challenging. It is a very challenging question. What can be said in the or if a Morse decomposition of the pullback attractor can be somehow analogously be done for at least in the case of sorry, I was just checking time. It seems that I'm running out of time. So what can be said about the pullback attractor in the non-autonomous case, or if any of this result can be carried out for that case? Okay, so what about state-dependent delays? I will tell a few words about this. So this is also very recent. It has just been submitted a couple of weeks ago, I think. Yeah, maybe 1 month. Okay, so now we have a scalar equation, but state-dependent delay. We have, I don't list all the conditions, but the most important ones are that we have a feedback condition, just as we had all the time. We have this third one is a dissipativity condition that guarantees that the global attractor exists. We have suitable phase space, and we can prove that even in this case, a global attractor exists, and not that it exists, not only that it exists, that's easy, but Morse decomposition, a very analogous Morse decomposition of the global attractor can also be given. And what is somewhat different here is that in this very general setting, where we don't really assume anything concrete about the state-dependent delay only, which maybe should be here. Yeah, here I corrected it. T minus tau of x sub t is strictly increasing for any solution x. So we assume this without knowing anything about the state dependency, which is okay. In general, we don't know what that means, but in the sense that you have to check this for if you have a concrete state dependency. Of course, this is not trivial at all, but in most of the applications, this is fulfilled somehow. Okay, and in this with this generality of the delay, we cannot really guarantee that V is finite on the attractor. So when we have this, I should have probably listed here one more bullet point, is that one more ingredient of this is that, which is related also to the absence of super exponential solutions, very closely related actually, is that the number of sign changes cannot be infinity on the global attractor. Moreover, it can also be shown that there's a uniform bound of, so V is bounded on the global attractor, so to say, which is highly non-trivial in general. But otherwise, if you would have just these level sets, there may be infinitely many of these, and that wouldn't give you a Morse decomposition, at least not to our, not in our definitions, where you demand that there are only finitely many of such invariant sets. Okay. Okay. So one way of handling this, so to say, problem that we may have even, or at least we cannot prove in this very general setting, that there are no super high frequency solutions. So there are no solutions which change sign infinitely many times, and not even speaking about the case when that we cannot prove that it's what would be more a stronger thing to do is to say that the V is bounded on the global attractor. So to overcome this, one can define this Sn plus Morse set, or N naught plus for a concrete N naught, which contains such entire solutions that remain, the number of sign changes, or the V values, to be more precise, stays above N for all times. Okay, and it turns out to be also to be compact and invariant, and it turns out that the Morse decomposition with these kind of sets, with any N naught greater than this N star, we get a Morse decomposition of the global attractor. And in concrete examples, to conclude very soon, I give you some examples where all the conditions are met. So if you take such a threshold delay, for example, where tau is defined by such a kernel function and an integral, these are called threshold type delays, then all the conditions will be met, and these threshold type delays appear in various models of, for example, immune responses and such. Or if we have, like with the position control with echo, such an implicitly given R. So for example, here, what we would, if we don't neglect this, how much we traveled, then how would this look like? Okay, so C is the speed of our signal. So we have, we can measure how much time was spent between our us sending the signal and receiving the signal. So we know actually the tau. I'm sorry, that should again be a tau. I'm very sorry for this. So C times tau is 2 times W. So this is distance of the origin and the wall, plus x of t plus x of t minus tau, right? So from this, you know the C, you know the tau because you measure it, and therefore you can calculate this this x sub t plus x sub t minus tau. Okay, and based on that, you can make your decision whether or how you adjust your velocity. Here you have access to your velocity to change. You can change in this control your velocity and not the acceleration. This might be less realistic, but nevertheless, this gives you such an equation. Okay, so this is such an implicitly given state-dependent delay. And you will need some assumptions on this function R. This last one is exactly to guarantee that, mostly to guarantee that it's strictly increasing, that the tau of x of t is strictly increasing. Okay, so it cannot be too fast. Okay, and in that case, you can give the Morse decomposition just as we did in this, how we did it here. But even more we can say, because in these concrete 2 examples, we can actually prove that the V is bounded on the global attractor. So you can even give a sharper result in that sense. Okay, so what are some? So that was mostly what I wanted to say. Maybe just a few words about what open problems remain. So it would be nice to find a joint proof for the existence of such Morse decompositions in a more general setting. So, like I showed you, there was already a result by Malay-Paré for scalar equation, negative feedback. There was scalar equation, positive feedback for by Monica Polner. Then I had, again, for constant delay but cyclic systems with either positive or negative feedback. Then there was another one for discrete time. And now there's this one for for state-dependent delays, but scalar. And I assume and I hope that we will be able to do this also for state-dependent delays, but for cyclic systems. But the nicest thing would be to give a common or a joint proof which would cover all these. And I think it's to some extent possible. So I think if one assumes that one knows some properties like the existence of the discrete Lyapunov function and its properties, then there are very, very similar parts of the proofs which could be covered altogether. The question of what Morse sets are non-empty are highly non-trivial. Usually what one can do is that related to the eigenvalues that are greater, that have real parts greater than 0. So technically for all n's smaller than n star, there will be a periodic solution in each Morse set. And this is done for the scalar case by Malay-Paré. But this is another technique, and it's also highly non-trivial, may contain topological arguments, which I'm not very familiar of. Okay, and like I already said, it would be very challenging to carry out such a result for non-autonomous case as well. Okay, these are just some very partial results for at least monotonic right-hand sides when one can show existence of periodic solutions of prescribed frequency. I also had some results related to that, and some other authors as well, which yields that some of the several Morse sets are non-empty. Okay, and the Morse decomposition is non-trivial in general in that cases. These are just some references I have talked about. This is the preprint which has recently been submitted, and like I said, some parts haven't even been submitted. Okay, so thank you very much for your time and for your attention, and also for the invitation again.
Okay, thank you very much, Ábel. Yes, let's thank our speaker, and then the mic is open for questions. So if you have any questions, don't hesitate to unmute yourself and just ask. So any questions from the audience? If not, then I will ask you to please show me the theorem on the new Lyapunov function that you gave us. This V of phi A. Yes, yes. I see. No, I was very confused because I was trying to apply this theorem to a constant delay. So I said, okay, let's say tau equals 1. And then I thought, yeah, and I may as well choose a equals 1/2. And of course, this shouldn't work as a Lyapunov function, right? But indeed, you
What
are
is 1/2?
measuring.
Sorry.
So if you pick sorry, minus 1/2. If you pick a equals minus r/2, for example, and you have a constant delay equals r, then I was thinking, well, yes, but v of xt1 comma minus 1/2, that's not a Lyapunov function, not a discrete Lyapunov function. But of course, you are performing the evaluation along tau of t, right?
Yes, here you have tau of t, and yeah, so this is exactly what you would get if you, with a time transformation, actually, you just stretch it all the time, stretch it or push it until tau of t is 1, okay? You
Yes.
can rescale, but that doing that directly seems to us to only work when you have that tau of t is differentiable. And for example, in this, yeah, in some cases it is. If you have, initially you have a state-dependent delay, it may or may not be differentiable, the
Yes.
tau
Indeed.
of x of t. And if also even in the, if you have directly, not, if this time-dependent time variable delay doesn't come from a state dependent delay, then you, of course, you can also have a time variable delay that which is not differentiable but only continuous, for example.
I see. But doesn't this imply that you should think of the phase space as continuous functions times time, essentially, times the reals or something like this? Because you're evaluating the Lyapunov function on the phase space, right? And now the phase space somehow includes time.
No, so yes, a good question. So the phase space is still, so the one assumption is that this tau is bounded by some r.
Yes.
And now you still have the phase space as defined, the continuous functions, one coordinate on minus r0 and the other is just 1 point. So this, the phase space is still the same. You can consider it like that, but when you count the number of sign changes, then it may count only on a subset. So if,
yes,
say you have, so when you have v phi a, phi is defined on minus r0 and some points, but then you just count the number of sign changes until a, which might be just minus r/2.
Yes, but in my head, this is a bit like a time-dependent Lyapunov function, right? Which is also a perfectly acceptable definition in ODE, for example, for a traditional Lyapunov function.
Yes, indeed. So this here it is. I don't know if we call it a discrete Lyapunov function or not, but definitely this depends not only on the state, but also how you count these sound changes depends on each on the solution itself. If you're just given one segment, you can only decide on.
Yes, so that's why I would suggest writing something like
well,
tilde, something like b tilde of a function of phi, for example, comma t, and then this is the composition.
But it doesn't depend directly on time, so it only depends on the state. So
I would say
given
it depends on time.
phi, sorry.
I would argue it depends on time because it depends on tau of t1.
Oh, for sure. Yeah, sorry, I was talking about the state-dependent case. In the state-dependent case, you don't, yeah, okay.
No, in state-dependent, I agree that then
Yeah.
it's time independent. Yes, so that's why I was a little bit confused, but otherwise.
Yeah, thank you for the comment, yeah.
Otherwise, I'm happy. now I think I begin to understand. Thank you. So are there any further questions from the audience?
May I have a question? Hello.
Of course, Yuki.
Hi, Yukiko.
Yukihiko. My question is not about the theorem. I'm curious how the cyclic system of delay equation with state-dependent delay. Well, actually, for constant delay case, I think the in the beginning we can think about the system of delay differential equation such that each component, the right-hand side of each component can have delays. But after that, suitably shifting each component, one can obtain a system of cyclic system of delay differential equation with just one single delay in the last component. Can we do the similar for state-dependent delay case?
Yeah, I fear not. Yes, so that's you touched a very sensitive point of this, or weakness of this, that you can somehow quite naturally, if I understand your question right, and I think yes, that so in the original setting, you can accumulate these calls in one, right? So with a transformation.
Yeah.
But if you have here all of them are state dependent, then the transformation will ruin everything. So I mean, you may have such an equation here with a time variable delay, let's say, but how this changes everything, so it kind of defeats the point then. If you originally have many state dependent delays in the original setting, but if you look at the normalized equation and then you put here a state dependent delay, that's okay. Yeah, but otherwise things get really complicated, and I'm not sure whether that would make sense to transform it. Even when it is possible, it's not clear what it would say for. Okay, so let's put it that way. You can transform it, at least when it's differentiable in t. What you get, the delay is differentiable, but then what does it say for your original equation is unclear to me, at least. That's the problem. What?
Yeah. I also don't have a good idea.
Yeah.
Thank you.
Thank you for the question.
No.
No, this seems to be a very complicated question, actually. Yes, I had not even considered that. But that's a very good question. Further questions? Otherwise, I would like to ask something else. So you told us about this at Sn plus, right, for the Morse decompositions, which essentially comes from not being able to rule out subsets with an infinite number, an infinite Lyapunov function. But then, isn't it fine also to just have an unbounded Morse decomposition in a sense?
Well, yeah, why not? That could also work, I think. But we took the definition for this. This traces back to Conley, I think, the definition of a Morse decomposition, and yeah, we wanted to fit it into that framework. But I also agree with you that it's most likely could also be done just to modify.
Yes, I mean,
relax
even though,
this condition. Yeah.
Even though the attractor is bounded, you could still have infinitely many more
Sure.
cells at the same, right?
Yeah, probably that could also work. That's also good.
And then because the
idea.
definition of more set only requires that you flow in one direction, well, as long as you have a well-ordered set, you're fine. A well-ordered set of indexes, right to say.
Yeah.
Good. So further questions? Otherwise, I think we may as well close the talk here. I mean, this was already a very complete, very in-depth talk about a huge history of topics related to cyclic systems. And yeah, I would like to thank the speaker again for giving such a nice presentation and for being so thorough in the analysis. And yes, I think we can finish the official part of the session here. And then if anybody wants to stick around and maybe chat a little bit, it's also fine. But I think we close this seminar here.
Thank you very much.
Thank you very much.
Thank you. Thank you very much. Yeah.
No, you really introduced us to something completely new. I'm really happy about this. Of course,
thank you very much for the opportunity.
I would also be very interested in knowing more about what solutions can live inside these more sets, right? Because I was thinking, yes, but say that now you stick within one more set. Do you have something like uniqueness of prehistory? Because this is something that you should have, or that you usually have in monotone feedback systems, uniqueness of prehistory, right? So you don't have to carry these that exist. So you have the burden of carrying these long definitions, right? There exists an entire function such that it takes this value at some point. Mm-hmm. But if you have uniqueness of prehistory, then you can just say yes. You just talk about the effect of the flow on a specific initial condition, even if it's in backwards time direction. You have.
Yeah, but in general, you don't have. In general, you don't have backward uniqueness.
Not even on the global attractor.
No, I don't think necessarily. Yeah, probably for monotonic systems, I don't know. Yeah.
I see.
Yeah.
And then, of course, there's a question of, well, your dropping condition is like a codimension 2 condition, right? Like 2 values are 0.
Yeah.
I see. Because there exists this obscure PhD thesis, Ignaz Tereshak, a really, really nice thesis from the 90s, maybe, where he discusses the discrete Lyapunov functions abstractly. So he says, let's say that they have these properties. And then somehow the dimensionality of the omega limit sets is given by the dimensionality of the dropping condition. So if you have, if you need to evaluate at 2 points to see the dropping, like in standard in the Malepari case, then the omega limit sets should be 2-dimensional. If you have to evaluate at 3, then the omega limit sets should be 3-dimensional, and so on. But I've never found a discrete Lyapunov function that has this codimension 3 property. I only know codimension 2.
Oh, that's very interesting. Would you mind sending me this reference you're talking about?
Of course. I will look it up and I will send you an email.
Thank you.
Of course, it's something that's kind of hard to cite because it's a PhD